All right, it's been quite a journey this year. We arrived in the jungle on our little beach. We did our rock, paper, scissors game. We got separated from the elves on the rope bridge, and then we got lost in the caves where we found the elephants, and then we came out and found the monkeys, and then we found the grove. And now we're about to end our journey in the grove where we're going to get picked up. Welcome to day 24 of Advent of Code 2022. Today, I'm going to be explaining the solutions to the puzzles of the second to last day of AOC 2022. I'll be going through my thought process, my solutions, my code. If you want to see my code too, that's going to be linked in the description below, so do be sure to check that out. Today was, I think, a relatively straightforward day. The leaderboard shows that rank 100 solved it in about 26 minutes, so it's not as bad as yesterday's. Actually, sorry, I meant day 22. Day 22 was the cube folding day. Yesterday's was pretty standard, I think. Yeah, it was moving the elves out. Okay, so today's puzzle, I'm going to be explaining everything, but first you're going to see me doing a time lapse. All right, today was a fairly straightforward state search day, so I'm grateful that there was a little less on Christmas Eve and I didn't have to spend hours on this. I did spend about 1 hour on this because I had a typo over here. Instead of writing n-2, I wrote n-1, so that was pretty sad. But anyways, let's explain the puzzles. Today we are getting out of there. So we've planted the seedlings that we did yesterday, and we are going to the extraction point, which is halfway up a hill. But we're going there, and then we come across a valley, and there are blizzards inside. So our goal is to navigate from the start to the end of this little valley while avoiding the blizzards. So how do the blizzards move? Every blizzard is described by an arrow, which describes the direction it's moving in, as well as its location. So every blizzard has a direction that's either up, down, left, or right, and it's somewhere within this valley. And we are given our input as this little ASCII art grid. Every minute, the blizzards update their positions according to their directions, so we just take wherever they are and we move them along their direction. If a blizzard ever hits the wall of this valley, then we'll wrap around to the other side, so this is due to conservation of blizzard energy. So we can see that if this blizzard over here is moving downwards and it's about to hit the wall, then it's not going to go into the wall, it's going to form a new blizzard up here in the next minute. Otherwise, they just continue moving in straight lines. Blizzards can also overlap because they are made of tiny snowflakes, so they just pass right through each other if they're in the same location at the same time. So actually the problem is we are starting at this entrance location, which is in row 0, column 1, and we're trying to get to the end, which is last row, column, second to last column. The conditions are that we can't move into the walls at any time and we can't move into a blizzard at any time. So we're moving simultaneously with the blizzards, which means that we have to look ahead and see if the location we're trying to go to is going to be occupied by a blizzard, not if it's currently occupied by a blizzard. So we just need to navigate our way to the end. This might involve some like shuffling around of location. We might double back and turn around because the blizzards need to be avoided, but eventually we will reach the end. And we need to find the minimum number of minutes that we need to reach the goal. Okay, so let me talk a little bit about how I did this through code. The basic idea is we need to figure out how the storms are going to move. So I'm calling them storms instead of blizzards because that was easier to type. And then we need to do like a BFS or some kind of state search to figure out the shortest path to the destination. So this is pretty well-defined parameters, unlike the cube day where we had to fold up a cube. That was a little bit less well-defined. But our plan of attack here is pretty clear. Figure out the state of the blizzards for any given point in time, and also figure out the BFS or Dijkstra's code. So at the beginning, we're going to just parse our input. That's pretty standard. We're going to insert all of the locations of the blizzards, or all of the blizzards themselves, into this set called storms. So how we do that is we just go through all of the coordinates in here. N and M are going to be the heights and width of our map respectively, so number of rows, number of columns. Iterate through all of those locations. If that location contains an arrow, so like one of those greater than or less than signs, or the carrots or the V, that's a blizzard, and we need to insert it into our set with the appropriate direction index. So I'm using same strategy as I think day 22 might be the cubes day, where we are enumerating. I don't know why I have a ders equals ders there. We're enumerating all of the possible location vectors or displacement vectors. That's going to be right, down, left, and up, respectively. And those directions are represented by 0, 0, 1, 2, 3 for right, down, left, up. And that's just going to be stored inside this array. So now we have all the storms inside a set described by the row, column, and direction. Direction is not going to change. Row and column might change. Okay, over here I have a few debugging functions. We can ignore those. Now we need to simulate the storms moving. So what we do is we go through 1 to the length of the period of the storm's positions. So we know that eventually the storm's locations are going to cycle because they kind of wrap around, and every storm either wraps around with a period of n-2 or m-2 because n-2 is like the length of the possible number of positions they could be in for their columns, and m-2, actually I said that in the wrong order, but you get the idea. So in this case, there's going to be 4 rows and 6 columns, which in total makes 24 possible states, or rather only 12 possible states that these can be in, because that's the lowest common multiple of 4 and 6. So there's 12 unique locations these blizzards are going to be in, so we can kind of reduce our computation by figuring out what that period is. That is the lowest common multiple of n-2 and m-2, as I said previously. So we're going to iterate from 1 to the period, which is just going through time. We're going to initialize this new set, which describes the locations of the storms after the current minute, and then we just need to simulate all the storms, go through all the storms, update their positions. If that position would run them into a wall, that's what all these if statements are for, then we need to wrap them around to the other side. So for example, if the blizzard would move to row 0, then it actually needs to wrap around to row n-1, because that's on the other side. Okay, same idea for hitting the bottom row or the right column or the left column. Any of those walls we can just handle with similar if statements. So after we've wrapped our location, the blizzard has updated its location and we know where it's going to be in the next minute. So we just add that to the new set, and then we can just record that new locations of the blizzards inside this states variable, which is going to be a list containing the locations of all the blizzards at any given time. So we're going to have, in this example, 12 elements in this list. Okay, and now we can start the BFS. I'm actually going to be using Dijkstra's here. If you don't know about Dijkstra's algorithm, I'm going to leave a link to it in the description. Basically, it's like a breadth first search. It's searching a state space, but we are prioritizing the closest locations first to search, because in this case, we might like loop around and double back, so straight breadth first search isn't necessarily going to work here. Actually, it might, but I'm not too entirely sure. I feel like Dijkstra's would be safer. BFS would probably work actually, but Dijkstra's would make it faster. I don't know. If I'm wrong, do correct me in the comments. I would love to see feedback. Okay, anyways, the idea is that we initialize this priority queue. Again, if you don't know what a priority queue is, I'll link to it in the description, to record our time and our location. So start is going to be 0, 1, because that is the coordinates of the entrance location to the valley. So this is our starting state, time equals 0, location equals start. And then we're just going to keep track of all the states that we have visited before, which is going to consist of our time and our location. So just to make sure we don't repeat. So we take off the top element from this priority queue. So actually this should be front, but terminology, variable naming, we don't really care about that here. So if we visited this state before, then we can continue because we've already looked at it, or we're going to look at it soon. Actually, it means we have looked at it before. So if we have looked at it before, then we don't need to look at it any further because we have already considered that possible branch. And next, what we need to do is figure out if we're at the ending location. So if our location is at the ending location, then we need to stop because we've figured out a path that has gotten us there, and we can just print out the time associated with the current state. Otherwise, we go through all possible future states. So there are 5. They are moving to the right, moving down, moving left, moving up, and staying in the same place. We need to check if each of those transitions are possible. So figure out the change in row and change in column. There are 5 possibilities. DIRS is going to be those 4 like directions, left, right, up, down. And we also need to add the choice of staying in the same location, which is going to be associated with a change in row of 0 and a change in column of 0. So go through all those 5 possibilities, figure out the new location that we want to move to, record that inside this variable. We need to check if this is a wall. So if it is a wall, if it is not one of the start or ending locations, or if the row is not between 1 and n-2. So the mistake I made here, typo, was n-1 instead of n-2, because n-2 is going to be the second to last row in this case, and we need to make sure our column stays between 1 and m-2, which is just between 1 and like the last column. or rather the second to last column. So if we're not inside that grid and we're not in one of the starting or ending locations, then we should stop, not consider this neighbor. Also, we should stop if there's going to be a blizzard occupying this location in the next state. We can just check that using our handy dandy states variable. We can figure out where the blizzards are going to be next state by looking at t+1 mod period. So for example, our period length here is 12. The blizzards are going to repeat after 12 time steps. If we're at minute, say 13, then this is going to wrap around to time equals 1 because the blizzards are going to just start cycling. So we figure out where the blizzards are going to be in the next state, and we check if our proposed location that we're trying to move to is inside one of those blizzards. We can check that by using a pretty simple for loop. Since the state of the blizzards is going to be not just the row and column for each blizzard, but also the direction that that blizzard is going in, we need to check in all 4 directions to see if a blizzard at the given location and the direction is going to be inside this set. Okay, so if none of that has happened, we haven't hit a wall and we're not going to bump into a blizzard in our next move, then we can go ahead and add it to the priority queue to check next time we hit the end. Okay, so my solution over here running on the test input takes just about 5 seconds to run. It's pretty fast. I think the bulk of the time is spent actually computing the states. I think there's 300 of them here because there's 20 rows and 150 columns. So yeah, it runs pretty fast. And now let's take a look at part 2. Okay, what we're asked to do here is we've reached the end, we've gone through the valley, but now one of the elves has realized that they forgot their snacks at the beginning. Oh no. So what we need to do now is instead of just going from the start to the end, we need to go from the start to the end, and then back to the start, and then again to the end. So this requires just a little bit of modification to our state search, in particular the end conditions. So we're going to keep track of 2 additional variables for our state search. Instead of just keeping track of the time and our current location, we're also going to keep track of whether we have hit the end already and whether we have hit the start after hitting the end. So the condition here is that this variable says, have we hit the end for the first time? This variable says, have we hit the end start for the second time? And then once both of those are true and we reach the end, then we can stop because that means we hit the start and then that means we hit the end and then we went back to the start and now we're at the end again. So just as a sanity check, we should never have this variable called hit start be true after hit end is still false, because we have to have hit the end first before going back to the start. So hit start doesn't mean have we reached the start, it means have we reached the start after reaching the end. So it's a bit confusing, the variable naming, but hopefully it should be clear. So in fact, I just made this assert statement to sanity check. We should never hit the start for the second time after not hitting the end. Okay, so the modification to our state search is right here in the if statements. So if we have hit the end, then we have a couple of possibilities. Either we are hitting the end for the final time, which means we have hit the end for the first time, gone back to the start, and now we're back at the end. If that's the case, then we can just stop and break. Otherwise, we haven't done that little loop. So we have neither hit this end for the first time and then gone back to the starts, or like hit the start. Basically, this is us reaching the end for the first time, and hit start should be false. In this case, we've reached the end for the first time, and we can mark that variable as true. The other case is if we are at the start, then there are a couple of possibilities. Either we are at the start for the first time, or maybe we're staying here for a while or coming back. But anyways, if we haven't hit the end, then there's nothing special to do here because we need to go to the end before going back to the start. So if we haven't hit the end, nothing to do. If we have hit the end already, that means we went there and now we've gone back. And since we've gone back, we can mark this hit start variable as true. So all these if statements, there's just a couple cases to go through. Just requires some careful thinking about, what part of the process you're in. Okay, and this just also requires modifying the transition a little bit. We only have one call here for modifying the priority queue. We just need to put in hit end and hit start into the state to make sure we're doing the transitions correctly. Okay, so that's it for day 24. Today was a fairly straightforward, again, state search, and all we had to do is first find out where the blizzards are going to be at any given time period, and then do a little breadth first search / Dijkstra's, where our transitions are validated by that little mapping from time to where the blizzards are going to be. because we need to be sure not to hit a blizzard at any point in time. So one thing that I've learned through doing AOC this year is just using sets is really, really OP in Python. In this problem in particular, I use sets to store the locations of the blizzards along with their directions, and that just helps me update a lot better than like storing them inside a two-dimensional array. Because blizzards can overlap, and looping through everything is going to be a lot easier when you only have an array that's the size of the length of that's the number of blizzards long instead of having to go through that entire 2D array. Okay, so we're almost at the end here. If you have any questions, comments, or feedback, do feel free to leave it down below and I'll take a look. As always, my code's going to be in the description, linked below, so be sure to check that out if you'd like. And yeah, that's it for day 24. I'll see you tomorrow for Christmas, day 25. Thanks for watching.